One, decided to make a little short physics talk. Some people may not have understood exactly what happened today in class, so I want to make sure we address the issue of where do the equations come from. And again, if you want to take notes on this one, it's not required. You should already have notes from today's class, but just for those who were absent, I figured I better at least share what we did today in class. So our learning objective is use data and graphs to explain where the equations come from. Basically today we are analyzing and interpreting data. We're going to be looking for patterns, and of course because we're dealing with numbers, you have to pay attention to some scale, proportion, and quantity. So here we go. So what we did today in class was we got our data and we looked at areas that looked good in terms of data. On graphical analysis here, you could see that what I asked the class to do was make sure they had a nice smooth curve for their position time graph, but then also a relatively straight line for the velocity time graph. And pick a time region, so here it's 1.5, this is 2.5, but pick a time region when it actually is good for both of them. So I wouldn't choose between 1 and 1.3 seconds only because this part does not look like the normal part that I expect to see. I expect to see a straight line. So I'm going to choose between 1.5 and 2.5, and I'm actually going to remove my velocity time graph. And what I ask people to do today is to do what is called a curve fit. So we apply a curve fit, and when we do the curve fit, because this is supposed to be a parabola or quadratic, we choose a quadratic on this list here. So choosing quadratic, it gives me a curve fit, we apply it, and what it does for me, it gives me information. It gives me the A value, the B value, and the C value for a quadratic. And we're going to use that in our slide. At the same time, what I asked students to do was to then analyze a velocity time graph, and this time the same time region, highlighting the same time region, 1.5 to 2.5 seconds, and we again do apply curve fit, and because this is supposed to be a line, we apply a linear fit, and you can see we get a slope and a y-intercept here. And what I ask students to do is actually share that data as a class. But before that, we ask them to actually create their equations. You can see that for knowing that this is y equals ax squared plus bx plus c for this, I plug in my number a, 0.3676, my b, my negative 1.546, and then my c, 1.981. And at the same time, just to give it meaning, oops, sorry, this is supposed to be an x here. Position is x, so I should have an x here because that is on my y-axis, it's not y. We physicists give meaning to equations by putting down what we actually are graphing. In this case, it should say x. And then on the y-axis, it's time. Sorry, it's being down here as time. And so instead of x squared and x, I put time on for my x-axis terms. Okay, so we plug that in, and so now we have an equation that looks like a quadratic, but now it's related to our position and our time. Likewise, we can do the same for the velocity graph. So with our velocity time graphs, we can do the same thing, again starting with y equals mx plus b. On the y-axis, we don't have position this time, we have velocity, and you can see me place a v in that spot. I go to my slope. My slope is 0.7337, so that matches there. And then my x, which is normally my x-axis, well, my x-axis is time, so I'm going to put t instead in that spot. And then, of course, my y-intercept, negative 1.556, becomes a negative number here. So then I get these equations here. So then what I ask the students to do is to then look at an Excel sheet that I posted on Google Classroom. And I asked them to actually put their slopes for their velocity times. Okay, so everybody's numbers is different than mine. You can see that their slopes here. And their y-intercepts as well. And you can see their y-intercepts are different than mine. Likewise, I had them put in their A, their B, and their C from their equations after they wrote it down in their notebook and put it in there for all the groups. This is actually period 3's data. And then we analyzed the data. First things first, I just want to remind you that in the velocity time graph, remember that the slope of a velocity time graph is acceleration. So we learned that early in the year. And so this number here is really telling me something more than just a number. It is telling me a piece of physics information. It is telling me that it's accelerating at 0.7377 meters per second squared, meaning every second it will increase in speed by about 0.74 meters per second. Okay, by about 0.74 meters per second. When we look at this equation, when it comes down to it, since velocity is acceleration for this portion of this velocity time graph, our equation becomes an A for that spot. Now what is this part here? Well, the y-intercept is really the velocity when time is equal to 0. So this is actually the time for when time is equal to 0. This is my velocity. So this is actually my initial velocity, and that's how we label it in the equation. And because this is initial velocity, then this has to become our final velocity in our equation. So this becomes one of our equations that comes from data. Okay, the data that we analyzed that gave us a straight line, and then we give meaning to the slope, we give meaning to the y-intercept, and the y-intercept is the initial velocity in this case, and the slope in this case is the acceleration. Likewise for this one here, when we compare these numbers, this is what we did in class, we compared the slope for this one and compared it to the A value for the equation, because the units on both of them were the same. 1.88, 0.96, 1.45, 0.72, 1.56, 0.69, 0.62, 0.32, 1.38, 0.67, 2.08, 1.04, 1.39, 0.68, and 0.96, 0.48. And when we looked at the pattern here and compared to the pattern there, everybody was starting to see that this number here was double this number. Or in other words, A seemed to be a half of the number over here, roughly. And again, this is real data, patterns you have to look at as a big time pattern. This is half of the slope over here, which means that this number here, if acceleration is what this means this number here represents half of the acceleration. And then when you look at this number on this column here and compared it to this column here, they both have the same units. You can see that they're roughly the same number, 1.81, negative 1.81, negative 1.80, 1.86. This one doesn't quite fit. Negative 0.70, negative 0.74, negative 2.14, negative 2.14, negative 2.78, negative 2.75, negative 2.36, 2.36, 2.33, negative 1.48, negative 1.48. So you can see that this data here seems to be the same, as it turns out. This number here also is supposed to be the same as this one, which is our initial velocity. And when you put it all together, the equation becomes this. This number here really means it's half the acceleration. So we write 1/2 a, t squared. This number here is the initial velocity, so it's vi times t. And of course, c is the y-intercept in parabolas. So just like this was the initial velocity when time equals 0, this is the initial position when time equals 0. And so this becomes our equation that helps us find distance for an object that's accelerating. And this basically shows you how equations come from data. We analyze patterns, we look at graphs, we analyze the shapes of those graphs to give us formulas and equations that it relates to, and then we look at the relationship between things to really give meaning to all the numbers and variables. Well, that's all for today. It's a short one. Hopefully that makes sense. If you have any questions, give me a call. Thanks. Or not give me a call, but come in tutoring.